Hi, my name is Yan Xia, and I'm a PhD student at the Technical University of Munich. I'm pleased to present our work SOE-Net for point cloud-based place recognition, which is done together with Yusheng Xu, Shuang Li, Rui Wang, Juan Du, Professor Daniel Cremers, and Professor Wei Stilla. In autonomous driving, relocalization in a large-scale 3D map is a critical functionality, and place recognition is a key subtask of this problem. The aim is to recognize the place where a given scan is taken. We would like to input the scan into the search box and get its location from large geotagged database. So to address this task, the common approach is to extract descriptors from the database scans. Then, given a query scan, we retrieve the best match, and the recognition is performed as nearest neighbor search in high-dimensional species. However, point clouds obtained from LiDAR scans are always noisy, and the scenes in different locations have a high similarity. So in this work, we present a data-driven, robust, and discriminative global descriptor. Our SOE-Net includes three main contributions: point OE module, self-attention unit, and a novel loss function. Here is an overview of our network pipeline. SOE-Net first extracts 3D local descriptors from the raw point cloud using a novel point OE module, and the global descriptor is then aggregated from the local ones with an effective self-attention unit. During inference, a code search retrieves the 3D submaps using this global descriptor. Next, we will explain the architecture of each module following workflow. As we know, the success of image-based place recognition is largely attributed to SIFT descriptor. Orientation encoding is a key property of SIFT. Therefore, we believe that encoding orientation into 3D local descriptor will be helpful. So we introduce the orientation encoding unit, which first adopts the select 8 neighborhood search to find the nearest neighbors for point P in each of the 8 octants, and then extracts features from 8 orientations using 3-stage convolutions. When aggregated into a global descriptor, we notice that different local descriptors should technically contribute unevenly. So we develop a self-attention unit to introduce long-range contextual dependencies, encoding the spatial relationships of the local descriptors for weighting. To train the global descriptor, all previous methods adopt lazy quadruplet loss. Lazy quadruplet loss aims to maximize the distance between the anchor and the negatives, and maximize the distance between the additional point cloud and the negative samples, but ignores which is the hardest negative point cloud. Therefore, we propose a novel hard positive, hard negative quadruplet loss, which picks the hardest negative point cloud and unifies the margin selection. We first find the hard negative point cloud, then we consider the future distance from the addition point cloud to negative samples. Finally, we select one of them as the hardest negative point cloud. The modification is simple, but notably more effective. Next, we will show some experimental results. Given a point cloud as a query, here are the top 3 retrieved matches. The top 1 match has a very similar thing as the query. Here is the location of each point cloud in the reference map. For the query, we can see the location of the top 1 result is correctly overlapped with the query location. The quantitative results are shown here. The left table shows our method achieved the highest retrieval success rate on the Oxford and RA datasets. The right table is trained on Oxford, RobotCar, US, and RA datasets. Our approach outperforms other methods on the R datasets. Here we show the recall curves of the top 25 retrieval matches. Both of our models outperform the other approaches significantly, especially for the top 1 result. Please refer to our paper for more experimental results. Thanks for your watching.